Hi, have you ever wondered why these pots have copper bottoms on them? Or which one takes more energy to heat up, this one or this one? Okay, so those are the questions we're going to answer in our next segment of Dr. Himsl's Science Channel. So stay tuned and we'll answer those questions. Okay, today's lesson is on specific heat and heat capacity. So, what is heat capacity? All right. Well, first of all, heat capacity is an extensive property of matter, which means that it depends on the type and the amount of matter present. All right. By definition, it's the amount of heat that is released or absorbed for certain temperature change. Okay, so if you remember, this triangle is the Greek symbol delta, which means the change in temperature. Okay, this is the heat capacity formula. So heat capacity is defined as C. All right. Q is a common symbol used in science for heat. You can use the units of joules or calories. All right. And change in temperature delta is T final minus T initial. All right. Now, usually it's a good idea to, because if you have if the final temperature is lower than the initial temperature, then you have a negative number. So just use the absolute value, and since it's a change in temperature that we're worried about. And plus, you can't have a negative heat capacity, so it doesn't make any sense. So just make the numbers positive. All right. When we're doing any kind of an energy measurement, it doesn't really matter what units you use. All right. As long as you know the conversions. All right. So you can use calories or joules. All right. So 1 calorie is 4.184 joules. Okay. 1,000 calories is 1 kilocalorie, or 1,000 joules is 1 kilojoule. So it doesn't matter what units you use. Just make sure you're consistent and you know what the conversions are. And treat the calories and joules units as base metric units, like you would grams, meters, and liters. So you can use the prefixes kilo, hecto, deca, deci, whatever. All right. Now, next question is, you're ready to cook some food. All right. So, which pot takes more energy to heat up, the small one or the big one? All right. What do you think? Okay. All right. If you pick the big one, you're correct, which makes sense, right? Larger, more heavy pot's going to take more energy to heat up. All right, so let's look at the two examples. All right, the small copper bottom pot requires 17,479 joules to heat up 50 degrees. And the larger copper bottom pot requires 77,963 joules to heat up 50 degrees. So if we did a heat capacity calculation, right, the small pot requires less energy to heat up 50 degrees, while the larger one takes more energy, which makes sense, right? Because the larger one is bigger, it takes more energy. So what is specific heat? Okay, now specific heat, on the other hand, is an intensive property of a substance, so it does not depend on the quantity of the substance. So in other words, if you have a drop of water versus a gallon of water, the specific heat will be the same, because it doesn't matter how much you have. That's what we mean by intensive. It does not depend on the amount present. All right, so here's a definition. All right, it's a measure of how much energy, heat, is required to increase the temperature of 1 gram of substance by 1 degree C. All right, so these are the common units. All right, you can express specific heat in joules per gram degrees C, or calories per gram degree C. Some people like to use degrees Kelvin. So it doesn't really matter, okay, as long as you're relating some energy unit to mass unit to temperature change, or temperature unit. Okay, here are the specific heats of some common substances. All right, I'm probably pretty sure your teacher, professor won't expect you to memorize the numbers, because you can always look those up, but it's always good to know water. All right, water's specific heat is 1 calorie per gram degree C, or 4.184 joules per gram degree C. So that's a good reference one. All right, iron, lead, copper, glass. All right, so others are usually listed in the appendix of most chemistry textbooks and handbooks. All right, so you can always look up the numbers if you don't know what they are, and then keep in mind the units might be different. You have calories, joules, kilograms, Kelvin. It doesn't matter. Okay, so just be consistent which units you use, and you should be okay. All right. All right. So this answers our question: why do companies that make cookware have copper bottom pots? All right. Well, let's look at our question. All right. So which substance requires the most heat to increase 1 gram of substance 1 degree C? Okay. So which requires the most heat? All right. Okay. So if you picked water, you were correct. All right. Okay. The higher the number, all right, the more heat or energy is required to heat up the substance, all right? So it takes longer to heat up and longer to cool down, okay? All right, substances that have low specific heats like lead and copper heat up quickly, but they cool down fast, okay? So the higher the number, the more energy or heat it takes to heat up. The lower the number, the less energy and heat required to heat it up. All right, here's another question. All right, if the same amount of heat is added to each substance, which heats up the fastest? All right, experience the largest increase in temperature. Okay, so which heats up the fastest? Okay, if you picked lead, that's correct. Okay, so lead has the lowest specific heat, so it takes less energy to heat up, so it's going to reach the highest temperature first, all right, and heat up more quickly, but at the same time cool down more quickly. So in reality, lead would be a better substance to use for cookware, but due to its toxicity, I don't think a lot of people would buy lead bottom cookware. So the copper is commonly used, and plus copper looks nice too when it's nice and shiny. Okay, so let's compare specific heats, all right, of the small copper pot and the large one, all right? So to calculate the specific heat, we'll take the energy value, which we calculated before, all right, divided by the temperature and divided by the mass. So the mass of the pot's 908 grams. Okay. All right, so the specific heat is 0.385 joules per gram degree C. All right, the large pot weighs 4,050 grams. Okay, so if we plug it into the specific heat formula, all right, it comes out to the same. So this further validates the idea that specific heat is an intensive property, so it does not matter how much we have, the specific heats are the same. Okay, so the heat capacities are different because there's different amounts. That's extensive property. All right, specific heat is an intensive property, so it does not matter how much we have present as shown in this example. All right, so in a lot of calculations we use the specific heat formula. So heat equals specific heat times mass times temperature change, which is T final minus T initial. Okay. All right, so heat, we usually use the symbol little q equals joules or calories. All right. Specific heat, we sometimes use the abbreviation C. I like to use the abbreviation SH because it reminds me of specific heat. All right, that's usually in joules per gram degree C or calories per gram degree C. Okay, mass is usually in grams. Okay, again, you can use kilograms if you like, but grams is common. And temperature is usually in degrees Celsius. All right, so we use this formula in calorimetry labs. All right, so these kind of experiments are done, in schools, colleges, universities, research facilities, food labs, etc. Okay. So now a calorimeter is an insulated device used to measure the temperature change when a sample gains or loses heat. Okay. So according to the law of conservation of energy, energy is neither created nor destroyed. It's just transformed. Okay, so heat lost of an object equals the heat gained by another object. Okay. All right. So we usually relate two specific heat formulas. So this would be the heat lost equals the heat gained. So you plug in the variables to solve for maybe an unknown quantity. All right, simple calorimeter, which is used a lot in schools, is just a regular styrofoam coffee cup and a lid and a thermometer. So that's pretty much all you need. All right. If you want something a little more sophisticated, you can use something like this. All right. Which is also, polystyrene, styrofoam cover thermometer. You can use a stir if you like to. So, all All right, so in thermodynamics, when we do calorimetry experiments, sometimes the reactions or processes that we measure are exothermic, so that's any reaction or process that increases the temperature of the surroundings, so heat is released. Okay. If you're in biology, some people like to refer to it as exo or exergonic. I've seen both spellings already, so you can call it that if you want. I like to use the word exothermic. All right, so here's an example. If you dissolve 1 gram of sodium hydroxide in 100 milliliters of water, the temperature increases from 25 to 50 degrees C. So if you see a temperature increasing or the surroundings get hotter, it's exothermic. All right, sometimes when you're doing labs, okay, the reaction or process might be getting cooler. All right, so that's when the temperature of the surroundings decreases and heat's being absorbed. That's called endothermic. All right. Again, to satisfy everybody, if you want to call it endo or endergonic, it's up to you. I like to use the word endothermic. Okay. All right, so examples: ice melting, water boils to form steam. Surprisingly, is also endothermic. You have to absorb energy in order to get the water to boil. All right. Please view my video on thermodynamics where I explain everything in more detail. But here's just a basic introduction for these slides. All right. So specific heat equations are a lot of times used to do heating curves. All right. So I have a video explaining the heating and cooling curves. All right, for substances, here's a cooling curve. All right, we'll talk about those later. All right, in thermodynamics too, we can measure heats of reaction, okay, or enthalpy of reaction. So here we relate the heat for reaction equals the sum of the heat of the products minus the sum of the heat of the reactants. Okay, so again, this triangle means change, which is delta for Greek symbol delta, which means change. All right, so if you plug in your numbers, if the answer is negative, it's exothermic. And if this answer is positive, it's endothermic. All right. So I have another video on this you can watch later sometime. All right, but I'm just trying to show where specific heat and calorimetry is used in other areas. All right. If you're doing reactions, all right, if you want to express a chemical reaction as endothermic, all right, you usually write the quantity of heat on the left side of the arrow with the reactants. Okay. Or you can express it as enthalpy with a positive, all right, which means that this much heat's being absorbed in order to convert to the product. So, all right, so this is endothermic. All right, in an exothermic reaction, heat is being released, so the heat quantity is on the right side of the arrow. Okay, so the enthalpy is expressed as a negative number, so negative 92.2 kilojoules. Okay, all right. So again, I have videos on this later. All right, so you can do those in more detail, but it's just to show you again where specific heat and calorimetry is used in various areas. All right, same with energy diagrams. Okay, all right, so we'll talk about those in separate videos. All right, now here's a problem that you should be able to do. All right, this is called a specific heat problem. All right, so let's read it. All right, the specific heat. All right, so whenever you're doing word problems, as soon as you see the word specific heat, write down the specific heat formula. Okay, that's how you do word problems. As soon as you see something that looks familiar, write down the formula. Okay, so the specific heat of aluminum is 0.900 joules per gram degree C. How many joules of heat are absorbed by 15 grams of aluminum if it's heated from 20 to 60? Okay, all right, so you just take the numbers, write the specific heat formula. All right, just plug the numbers in. Okay, do the math. All right, so make sure the units are the same. So grams cancel out and degrees C's cancel out. So the answer is 540 joules. All right, all the numbers have 3 significant digits, so the answer should have 3 significant digits. That's why I put a decimal there. Okay, so again, pay attention to significant figures. If you need a little review, I have a video on that too. So always maintain your significant figures when you're doing your calculations, and also always put units, right? So make sure you always put the unit. In this case, the unit's joules. Right. So if you're doing other specific heat calculations, all you have to do is just rearrange the equation. So in that problem there, we just plug these in. If you want to solve for specific heat, just take the mass times the change in temperature, divide Q heat by that. Or if you want to just find the mass, bring specific heat and change the temperature over here. So just rearrange the equation. That's pretty simple to do. Okay. All right, now here's a common lab experiment. Okay, using a calorimeter. Okay, so again, just to review, a calorimeter is an insulated device used to measure temperature change when a sample gains or loses heat. Okay, so heat lost equals heat gained. All right, so always remember that. All right, so here's the experiment. Let me zoom out a little bit. All right, so this is a typical calorimetry experiment that most students, pretty much all over the world, do in the lab. All right, so what you do is you take your calorimeter, all right, usually coffee cup thermometer. You can use a stir. All right, in a separate setup, you set up a Bunsen burner or hot plate. You know, heat a beaker of water with a thermometer. All right. Okay, and then what you do is, okay, before you start do anything, all right, measure the amount of water and weigh it. All right, so in this case, I weighed 100 grams of water in here, which would be 100 milliliters. Usually you weigh that. All right, and then you measure the initial temperature of the water, which is 20 degrees C. Okay, so you do that first. All right, so heat this up. All right, usually get it to boiling. All right, so what you do is you weigh the metal piece first. Okay, so I recorded 43.48. All right, measure the initial temperature of the hot water. Okay, so in this case it's 98 degrees C. All right, now since the metal is in the water, the metal and the water have the same temperature. Right? So this is the initial temperature of the metal. It's also 98. Okay. All right. So this is why water is commonly used in these experiments, because it's you know, specific heat's known. You know, it's readily available. It's cheap, so you know, it's a good material to use. Okay, so after you've done that, then what you're going to do is quickly put the hot metal into the calorimeter. All right, so you put it in quickly so it doesn't lose heat very fast. So, okay. All right, so none of this has changed, all right, yet. All right, so put the hot metal in there. All right, the water is still 143.48 metal. All right, here's the initial temperature. Okay, so once you put the metal into the water, all right, the temperature is going to increase. All right, once you put the hot metal into the calorimeter, all right, the temperature of the water increases a few degrees, you know, because you're putting a hot object in the cooler water, so the temperature is going to go up. So it may not go up a lot. So my example here only goes up 3 degrees. All right. So when you do these experiments in the lab, a lot of times don't expect a large change in temperature. Maybe, you know, a few degrees is probably all you're going to get, you know, depending how much metal you use. So, okay. Okay. So now we can plug in the solve the specific heat formula for this side of the equation. All right. So the heat gained by the water is, I use calories here. All right. Specific heat of the water times the mass times the change in temperature. So the temperature of the water increases because you put a hot metal into it. All right. So do the math. All right. Everything has 3 sig figs, so the answer should have 3 sig figs. So we calculate 300 calories. Okay. So heat gained by the water equals heat lost by the metal. Okay. So 300 calories equals 300 calories. Okay. Okay, so from our calculation, the heat gained by the water is 300 calories, and the heat lost by metal is 300. So the amount of calories is equal due to the law of conservation of energy. Remember, energy is neither created nor destroyed; it's only transformed. All right. I kind of like to compare this to spending money. Okay. So if you're spending money, what are you doing? All right, you're losing $10 and you're giving it to somebody else, right? So you're losing 10, but somebody else is gaining 10. Okay, so it's kind of the same idea with heat and energy, right? One thing's losing the heat, the other object is gaining the heat. But in the meantime, I'm going to keep this $10. I need it for stuff. All right. But in any case, all right. So rearrange the specific heat equation to find the specific heat of the metal. Okay. All right. So this is the specific heat equation now for the metal, right? So the heat of the metal equals specific heat of the metal times the mass times the change in temperature. Okay. All right. So I'm going to rearrange the equations. I want to solve for this. I'm going to divide both sides by mass times change in temperature. So specific heat equals the heat, all right, divided by the mass times the temperature change. Okay. So just plug in the numbers. Okay. So 300 calories divided by the mass of the metal times temperature change. Now note the T final minus the T initial is negative, so just make it positive. It makes it easier to do the calculations. Okay. All right. So I like to use absolute value. Okay. You don't have to use the negative. All right. Makes it less confusing and easier if you just change everything to positive quantities. All right. But anyway, so the specific heat for this calculation came out to 0.092 calories per gram degree C. So go back to slide number 7, and that matches copper. All right. So that would be our answer for that. So again, if you want to change the calories to joules, all right, just multiply by 4.184, and that would give you joules per gram degree C. So congratulations, you're now all experts in specific heat and heat capacity concepts and calculations. So thanks for watching, and please subscribe and watch for other instructional videos on the Dr. Himsl Science channel. Okay, so always remember you can do it. All right, be confident in yourself, and just be positive. Okay, have a good day, and I'll see you all soon.